So let's start. So our first speaker this afternoon is Professor Ferenc Iglói. I hope I pronounce well because Hungarian is one of the toughest languages in the world. He's from the Institute for Solid-State Physics and Optics at the Wigner Research Center in Physics is in Budapest. Also affiliated with University of Szeged and the recipient of such an high prize. He is a leading theoretical physicist in statistical physics, but especially with major contribution in disorder system, quantum spin chain, phase transition, collective behavior of many body systems, so all the stuff we like a lot. And today he will continue his lecture on disorder and order in quantum system. Possibly he will tell us what happens in higher dimension, if you understand. Ferenc, the floor is yours.
Thank you very much, Antonio. Thank you for this nice introduction. Indeed, I am going to continue my talk, and here is the last slide of my yesterday's talks, where I showed how the strong disorder renormalization group works for the one-dimensional case. So just to quickly remind you, it is a local renormalization. You do the renormalization actually in the energy scale. So you have your parameters in the Hamiltonian, the couplings, and the transverse fields. The largest value, the largest parameter. And depending on if it is a coupling or it is a transverse field, you will have a different type of transformation. For a very strong coupling, you will have a composite spin variable in the presence of a new renormalized transverse field. And in the opposite case, if it is a large transverse field, then this site is eliminated. And between the remaining sites, there is a new coupling which is generated. So this is the one-dimensional case when the topology remains the same. From a chain, you get also a chain, and you reduce the energy scale to 0, which corresponds to the fixed point, which is an infinitely disordered fixed point, actually. And this has been solved analytically by Daniel Fisher more than 30 years ago. And the question that you already posed, that what is going to happen, just a minute, what is going to happen in higher dimension? Actually, in higher dimension, you can do the same type of steps, just the topology is somewhat will be different. Let's consider a two-dimensional square lattice. And here, if you have a strong coupling, the strongest coupling, then after renormalization, these two sides will be a composite spin, and you will have a renormalized transverse field in that side. On the other hand, if you have a strong transverse field, then this side will be eliminated, and new couplings are generated. But you see that in that case, due to the topology, you will generally generate several couplings. So the number of couplings is increasing. And now if you go to apply this type of machinery, you also have to take into account the possibility that between two sides, or already there could be a coupling. So then there are two couplings, the new one and the original one. Here we use, which makes the calculation simpler, the maximum rule. So we take the largest one between these two. This is justified by the fact that if we have an infinite disorder fixed point, then these two parameters will be completely different magnitudes. So actually the largest one will be practically the same as if we would have the sum of these two. So this is the way how we proceed. And if we make the traditional algorithm, so we make this renormalization as we described, then at some point there are plenty of couplings which are included in this graph actually. And this makes the algorithm quite slow. However, you can think about, and actually there are several couplings which will never be used or considered later steps, since due to the renormalization, this will be eliminated without considering their values. So actually you can reduce the number of steps. And if you are clever enough, as my former student István Kovács made this, then one can have a new type of algorithm which each step just will reduce the number of sites, and the time which is used for the calculation of at the last step is scaling with the size of the graph or the system, which is n, as n time log n, in contrast to the traditional case when it goes as n to the power of 3, actually. So, but the two algorithms may give exactly the same final value, just you are much faster in this new type of algorithm. And what you actually have, that you will have actually a structure of clusters. These are the clusters which are in some way not connected, but will be decimated at the same point. Let's say here you see this, very probably this is the largest such cluster, which is denoted by this red color. This is not fully connected, since here in between, let's say one or two sites is eliminated already before, but the new couplings what we have make a connection between those. So this is actually the way what we have. And the same type of picture is seen for a larger system, so for 512. And actually, if somebody has a background in percolation theory, like our chairman in this type, so he knows that this type of a problem can be actually studied with what we know actually from percolations. So we take the largest cluster, which is in that case very probably this red one, and we make the following calculations. This is a fractal object actually, and calculate the fractal dimension. Having the fractal dimension, the magnetization will be given as L to the power of the fractal dimension minus the dimensionality of the system. So this difference will actually give the minus of the magnetization exponent here. The next step, that the extension of the cluster, so will give a length scale, which is actually the correlation length. Psi, and depending on the distance from the critical point, you can see the increase of this correlation length, and in this way you can define this exponent nu from this quantity. And then, since we have a quantum system, here we have also an energy which is connected with such a calculation. you calculate at the last step of the renormalization of the energy scale. And actually, the logarithm of this energy scale will be a power of the size of the system, and this psi will be the exponent what we have in this case. So having such a calculation, we could have actually a complete information about the critical behavior of this higher dimensional system. We can calculate even more. We can calculate also the entanglement. So in the entanglement, we have two parts of the system. Let's say this is a square, or the inner square, this smaller one, will be our system, which is shown by this letter A. And the environment, this outer part, is the environment which is denoted by B. And this entanglement is quantified by the von Neumann entropy through this reduced density matrix. And in this strong disorder case, actually you can easily notice that there is an entanglement between the two parts of the system if under the renormalization there are clusters which have parts in both parts. So all those which are here in this surface or interface, these will contribute, and actually each contribute by a value of unity. So you simply should calculate the number of these clusters here. And actually this will naturally be proportional with the area of this interface, since this number of these possible positions are all in this interface. So it scales if L, small l, is the size, linear size of the system, that L to the power of d minus 1. However, due to the corners what we have here, there are logarithmic corrections. And these logarithmic corrections are, how to say, in the one-dimensional case, it is very interesting, since the prefactor itself is proportional with the central charge of the Virasoro algebra. So here you can get a quite nice way to obtain this value of C, even if this is not usually a conform invariant system, but this can be interpreted as an effective central charge. And for higher dimension, the corner contribution will be also logarithmic. And these prefactors will be universal in the sense that having different type of disorder realizations, at the critical point, they have the same value. So this is what we could have for about the entanglement. And then we could make calculations of more local quantities learned from the theory of critical phenomena. We could calculate the magnetization at the surface of a semi-infinite system, let's say, or we can calculate it at a corner, as we here see, or at an edge. And for each one, we know that the local order parameter, the local magnetization scale with a given exponent, which is the surface, the edge, and the corner exponent, which are specific for the given problem. And actually, also one can calculate the magnetization profile, fixing, let's say, the spins, let's say, here in one surface and calculating it. And the obtained quantities, this exponent what we here have, and the decay exponent as the profile is showing this decay, they will be also universal in the sense that for the different type of disorder, they will have the same type of same value. So here we can see that for two different type of disorder fixed on box type distribution, we have the same slope, let's say, which gives actually for us the corresponding local exponent. And here you can have some table of data for different dimensions. Actually interesting that this infinite disorder critical behavior is valid as we noticed in any dimension. So actually the upper critical dimension is infinite. So in that respect, it looks like similar behavior as in Anderson localization, in which case also the upper critical dimension is infinite. Okay, so that's what we can say, and as a summary of this, we can say that for a large class of random systems where we have the nearest neighbor coupling, we observe that the critical behavior in these random quantum systems is infinitely disordered. And actually the disorder fluctuations, which are absolutely dominant, and using the strong disorder normalization at the fixed point is asymptotically exact. This can be calculated analytically at one dimension. In higher dimension, you can make numerical calculation, but as long as you can make this numerics more and more accurate, you expect to approach really the true critical point. The true critical behavior. The next point that what is going to happen if we have some type of relevant perturbation, and in the next time I will focus on this for long-range forces. We know from the theory of critical phenomena that the critical behavior also depends on the range of interactions generally. Also many-body interactions, so this could also be different if you have just two-body interaction or you have, let's say, three-body interaction or even more body interaction. And what is going to happen if you have an extra degrees of freedom, let's say, also longitudinal fields in the problem. Okay, let's go to the problem of long-range forces. And the corresponding Hamiltonian is very much similar as the previous one. Just the interaction term is long-ranged in the way that the interaction decays as a power of the distance between the spins, and having an exponent alpha, which should be larger than the dimensionality to have an extensive energy. And usually this prefactor of B and the transverse fields are identically distributed and independent random numbers. And for such a system, as I showed in the previous talk, there is some possible relation with this lithium, holmium, yttrium, fluorium system, which has some relation with this type of problem. It is also a dipole diluted ferromagnet. Okay, here we can apply the numerical strong disorder renormalization group, what I just showed before in the higher dimensional case. And here the first step is to identify the critical points of the system. To identify the critical points of the system, we use the way to define finite size critical points. So in percolation, in standard percolation, we know that at the spanning of let's say, a given square or a given finite system will define actually a finite size spanning critical point. Here we do a bit in a different way, but we also obtain size or sample dependent critical points. We use the following. We have the original sample, and we have actually an identical one. And we compare and we make contact the two, and we make a renormalization of this connected two systems, and we look what is going to happen at the last step. And actually, the renormalization will depend if this parameter, which is the log of this transverse field, it is the h typically is a small value. If this is the case, then the system, the last decimated object will be actually a coupling. So it means that the two objects will be connected to each other. However, if you are in the large H limit, then after making this renormalization, this will be renormalized independently. So somehow there will be no connection between these two. So the last decimated decimated parameter will be just a transverse field. So in this would mean that the system is in the paramagnetic phase. And we can locate actually the very point where this change will take part. And actually for a number of samples, so we have several 10,000 of samples, we will have a distribution. And the distribution of these pseudo-critical points for this case is shown here for different sizes. And as can be seen, this distribution has a shift of the maximum, and also the width is also shrinking with the increasing size. And we can have a good scaling collapse if we notice actually both the shift and the width of the distribution scales with one of the logarithm of the system. This is quite unusual, since conventional scaling works in a way that both the shift and the width is a power of the size of linear size of the system. And actually this the exponent what we have here defines the corresponding exponent, which is the width and which is the shift and the width exponents. And usually these two are the same in normal disorder systems. Here, actually, we have such a slower and a logarithmic behavior. And if we say that the size actually corresponds to the correlation length of the system, then the correlation lengths will have a Kosterlitz-Thouless type behavior in that systems. Which is just to be opposed with the behavior of the correlation lengths in conventional scaling, which is in a power law behavior. Okay, we can also calculate the frequency of the bond and field decimations at the critical point. So we have calculated the position of the critical point, and we make this renormalization. And it happens that actually more the fields are eliminated than the couplings. So usually you eliminate several transverse fields before you have a large bond which you can eliminate, and you go on in this way. And as L is going on, it will be more and more frequent that fields are eliminated. And this is just to contrast with the short-range system where these two are in the same order. So fields and bonds are eliminated in the same way. One can calculate the average magnetic moment. Oh, pardon. The average magnetic moment, which is not scarce as a fractal case in the short-range system with the fractal dimension as we saw before, but it also goes logarithmically. So actually there will be a different type of scaling. Here you will see actually how the magnetization with the system size scales if we take this log square type of dependence. So in that case, we indeed have a straight line as it should be if this relation is fulfilled. And actually, the magnetization will be quite small in this system. So in one-dimensional case, if we have a system of more size than 8,000, and actually at the very last step, the largest cluster will contain just 32 spins. And actually, between the sides, you will see here is a logarithmic scale that the distance between neighboring sides that you eliminate, there will be, let's say, one which is extremely large. It is probably has a length more than 4,000 actually. So here you always eliminate transverse field before then you will have an elimination of a coupling in this system. So this looks a quite unusual scaling in this disordered system. If we look for the energy scaling, this is the distribution of as the gaps as it is defined as the last decimated parameter. You see that in a log scale, this has a linear dependence. So it means that actually, and you have the same, it is in one dimension when you have large systems, and in 3 dimension when actually the system size are more moderate, but also you have such a linear dependence, which would mean that the energy and the size is related as in the normal conventional scaling. So having a z dynamical exponent, which is actually finite. It is in contrast with the behavior in the short-range system, where this, in this case, the logarithm of the energy scale grows as a power of the size of the system. And if we calculate at the infinite disorder fixed point, then as we know that in the short-range case, this formal dynamical exponent is divergent. But in this case, if we make the calculation, it will be actually very much close to this alpha. You remember the alpha is the decay exponent what we have. So this is what we see. And if we want to check the renormalization group flow diagram, we will have the following picture. R, what I show here, it is just as before the ratio of the bond and the field decimation. As we mentioned that this will goes to as 1 over ln L square. So with increasing size, it will be smaller and smaller. So at the fixed point, we go down to this line. So this line represents the fixed point. And we can actually measure the distribution of the end transverse field, and this will define this dynamical exponent what I shown in the previous transparency actually. And you see that actually you will have the following phase diagram. that the fixed points are at r equals 0. So this is when the size of the system goes to infinity. And actually, when this alpha over z is larger than 1 in this case, this is the paramagnetic phase. And this is a stable one since it is attracted. At the other side, however, this is the ferromagnetic phase here, which is unstable. So here the trajectories goes upwards. And at the critical point is just the z is equal to alpha, as I mentioned before. So this is what we see. And actually, if one thinks about why this exponent at the critical point should be alpha, one can understand, since if you make the renormalization, then actually between two remote points, actually there are always couplings which decays with the distance as 1 over r to the power of alpha. So actually, at the critical point, even if you always should decimate transverse fields, but the decimated new couplings are always much smaller than this already existing long distance one, and just you will decimate it if you in the length scale will reach this type of size actually. So that's why you will find this one. And actually, at this point, you will have a diverging correlation length. If you make more refined calculation of the magnetization, you will observe a jump in the magnetization, and actually you expect to have a mixed order transition. So for this long range system, the transition is expected to be not this infinite disorder type, but more conventional one, and even this mixed order or hybrid type transition with diverging correlation lengths, and at the same time with discontinuity in the magnetization. Okay, and now let's go to the second problem. What will happen when we have many-body interaction? So models with many-body interactions are known. Probably the best known is the classical example is the Baxter-Wu model, which is a triangle lattice Ising model with three-side product interaction, which is solved exactly by Baxter and Wu, and actually they calculated the critical exponent exactly, and this, which is believed to that the same for the four-state Potts universality case actually. The quantum example in this case is very probably several people have the idea to introduce this one. One of the first one was our late friend Loïc Turban from Nancy. He showed actually that this quantum model, which actually the transverse field Ising model with multi-side product interactions here. So actually, depending on the value of m, you have more and more sigma z here involved in this product. For m equal 2, we have the traditional Ising model, transverse field Ising model. For m equals 3, one can easily show that this has a degeneracy in the ground state 4. So it is expected to be in the four-state Potts universality class. And for larger values of m, it is a first-order transition. This is the case, at least in the pure model. And now we ask the question, what is going to happen if these couplings and the transverse fields are random? And I have to say at this point that for the transverse field Ising model, it has been shown that other models which have a discrete symmetry but nearest neighbor interaction, like the quantum Potts model or quantum Ashkin-Teller model or quantum clock model. In this case, the random systems has the same type of universality as the Ising one. So actually the Ising universality class for the nearest neighbor model seems to be very robust. And now the question, what is going to happen if we actually have this many-body interaction here? Okay, but here, unfortunately, the traditional strong disorder renormalization that I showed before does not work. Simply, if you make this renormalization, unfortunately, many new couplings many new parameters are generated during renormalization, depending, since here you have several positions. So depending on the relative position of the coupling and sides, you will have different type of parameters. So, and this number of parameters will increase with the renormalization. So it cannot be made in such a way. However, we can make some approximate renormalization by this block renormalization approach, which is somehow a bit older than the strong disorder renormalization, but in some respect it is quite similar. So the essence of it, that the Hamiltonian, what we have, is divided into two parts. One is the non-perturbed one, which is given by separated blocks. And there is perturbation which actually contains usually parameters which makes the connection of these blocks. And you solve exactly the separated blocks, which are finite. And then the perturbation is treated, this type of red term is treated perturbatively. And you make this type of calculation using a renormalization when you ask to have the same matrix element before and after the renormalization. Actually, this type, you can define in different way of the blocks and the perturbation, how you separate it. It seems that the quite a nice way of the separation is due to Fernandez Pacheco more than 40 years ago, actually, when this is actually a self-dual one, in which case here I show the coupling. This is the nearest neighbor problem, when the perturbation and the non-perturbed part are actually equivalent. And in that case, the system is self-dual. This will preserve actually the self-duality point, which is the critical point of the system. And turns out actually that this renormalization by chance gives you the exact results for the nearest neighbor model. Even if you have disorder, one can show that the typical correlation length exponent is 1 and the average is 2, as it is given by the Fisher calculation by the strong disorder and normalization. And we will go to use this method for the multi-site model. We use it for the m=3 case. So when there are products of 1, 2, 3 spins. And here also we use this self-dual separation. And we solved actually these blue parts, which has actually a block fixed the two ends. And here actually you have a coupling and a field. So it is quite easy to solve. And you can calculate the local magnetization in that point. So from this calculation, actually this is given by this formula, elementary calculation. You can make the same calculation in the other point here. This will give you then the magnetization in this point. Actually, it depends on the actual value of these parameters. And actually, if you calculate then the renormalized value of the coupling, then you ask the question that between the remaining three spins which are here, which is the interaction? So this interaction actually should be the same in terms of these parameters. So this, and this, with this renormalized value, with the average value of the original one. The average value of the original one is here, having the average value of this side, which is just this magnetization. This is a fixed spin, so this will be this value, and the magnetization here. So you will have a very simple form for this transformed value of the coupling. And you can do the same for the transverse field. Actually, using the duality, you have to simply replace the couplings and the transverse fields. And what you will have actually the following, that you calculate the transformed ratio, the ratio of the couplings and the fields. And it happens that actually it will be the product of the three couplings before. So it is seen that if it is the pure model, so these couplings are all the same, then you have a simple renormalization that the renormalized value is just the third power of the original one. From this, you immediately see the fixed point is 1, which is the critical point. This largest eigenvalue of the transformation is 3, and from this the critical exponent is ln2 over ln3, since the block that we used here to increase the size was 2. So in this way, we get a result which is not far from the exactly expected results for new equal poles. It is 2/3. Okay, now let's go to the terra incognita. This is the random model. Actually, in the random model, you will have the same form. Just if you repeat this renormalization to the next step, then you will see that these are the renormalized couplings. So you write these points here. And then you make once more the renormalization that at the surface sides, this one and this side will appear twice. Once from this one and once from this middle side, and here the same. So it is represented twice. And if you go on with, if you go on with the renormalization, you will have multiplicities of these couplings. So it means that if you iterate the process n times and you consider the logarithm of the renormalized coupling, of the renormalized ratio, then it will be actually some of the renormalized, or some of the original couplings having some multiplicities. So this will not be the usual way of the sum of random numbers that we have usually, that we have in in the case if we have the Gaussian distribution, but we have non-trivial way of multiplicities. Actually, these multiplicities can be estimated in a way that actually the size of the system in each renormalization step, we eliminate half of the size. So the size is 2 to the power of n, actually scales in this way. At the same time, actually, in each step, we generate 3 couplings. So actually, the sum of these multiplicities will be actually 3 to the power of n. So from this, we get that the typical value of this multiplicity is growing as a 3 over 2 to the power of n. So it is also will be a very large value. And from the fact that somehow the sum of these will give the total number of couplings here, you will have an approximate relation that actually that this number of multiplicities will grow as the 3 over 3 to the power of n. Okay, and this type of scaling, what we have here, the c multiplied by 2/3 to the power of n, and here the n multiplied by the inverse of this, and plotting this for different values of n, large values of n over 20. So you have huge, large, several million sites actually in this renormalization. These are quite close to each other, so these are not too bad. So if you then make all the calculation with this one, you will end up with the final result, what I show here, that actually the typical correlation exponent will not be 1 as we saw in the nearest neighbor model, which was 1. Here is ln2 over ln3. And the growth of the fluctuations are also, the log couplings grow as a power of the size of the system, but the corresponding exponent what we here have is not the 1/2 as we have before, but it is a different value. So actually we have the result that we have a new infinite disorder universality class in that case, which is quite unusual. Okay, so now I think I am at the end of my time, so I skip the last example about the use of the logarithmic field, and then I just go to the conclusion. So actually, what you can have as a take-home message that for random quantum system, if there are nearest neighbor interactions that and you have discrete order parameter and non-correlated disorder, then usually one has a random transverse Ising model infinite disorder universality class. Actually, the upper critical dimension is infinity, and this is also valid for other problems like the random contact process. Okay, and if you have some kind of perturbation, it could be relevant. For long-range forces, you have the traditional strong disorder scaling. However, as I showed, this is a mixed order transition with Kosterlitz-Thouless type scaling. And if you have many-body interactions, that a new infinite disorder fixed point is present. And but I had no time to present. If you have also extra longitudinal field, and you can show some reentrant transition behavior in this system. Okay, thank you very much for your attention. Here are just a few people with whom I worked in these problems. Okay, thank you very much.
Okay, thanks. So we will have. Oh, there is a way of clapping virtually. So I clapped just
Thank you.
the other way. Questions. Let's see if anybody. I don't know, because in theory one should raise hand or just open the mic if for questions. Otherwise, I already have some questions that are less related to the theory, but for me, I mean, I'm teaching a course in which it's very interdisciplinary, and one of the field where you apply these random models is machine learning. So essentially, you have this Boltzmann machine that are essentially your random models in which you have optimized the connection in order to get results. And one of the problem of these machine learning models that they are huge, they use a lot of parameters, and they try to reduce them. I would be very curious. So more than a question is this is a thing that I think would be interesting to see. If the renormalization group helps to reduce the dimensionality of the system. Because if your renormalization, you are able to get to a system with less bonds, less spins that still makes the right calculation, that will be a great advantage.
Mhm. Okay, so actually, perhaps I cannot directly answer to this question. Just showing that actually, as you perhaps I go back to the higher dimensional case and the typical here you see, let's say this is a two-dimensional one.
Yeah.
If you look the structure of this relevant cluster for which you get all the information, it looks very much chain-like or one-dimensional. And actually, the results of it will be that this exponent of psi, but you have here is not very much depend on the dimensionality of the system. So it seems that the relevant degrees of freedom or which actually govern the energy scaling of the system, these look practically quasi one-dimensional. So in that respect, you could, and this is the same actually in higher, even in 3 dimension. So this could actually be some kind of possibility to make an effective model, or how to say, if you just want to speak about this problem, you enough just to treat this very system, but you can perhaps make even simpler in some way.
Yeah, but for example, for me, I would be curious to simulate the models at various levels of renormalization and see how much they agree. Because that would be already very, very, very strong. And the fact that you see one-dimensional seems that you can compress a lot of information, but it's really to explore. I mean,
Yeah, sure. So it depends very much on this on the system, and I don't know if one can have a really a good argument why it should be like this. Yes, but this is the what one see numerically. That's right.
okay. Other questions?
Yes, may I put one?
Yeah.
Ilko? So thank you for the lecture, Ferenc. The question is with respect to lower and upper critical dimension. So when you started your lecture, you showed us zero temperature quantum fixed point, telling that it's a quantum system and it will correspond to classical thermodynamic phase transition in D equals 2. And my question is about upper critical dimension. For the thermodynamic phase transition, say in this universality class, in Ising universality class, I have D equals 4 with logarithmic corrections and then mean field. Do I observe something similar here, but in 3-dimensional system?
No, actually, here the unusual thing that actually here the upper critical dimension looks infinite. So actually, the question whether you have infinite disorder scaling or not. So we made the numerical calculation actually in 4 dimension, which showed that actually you have a other class of critical exponents. But we also used some kind of a scale-free network for which one expected the corresponding effective dimensionality is actually infinite. And making the calculation also such a network, we could show that this infinite randomness will survive. Actually, will not somehow this relation, which is here, that log epsilon is L to the power of psi, this will perhaps change to a log L to the power of something, or like this. So it seems that this type of a behavior stays. But this is not completely unusual, as I mentioned, that for Anderson localization, which is also a problem of quantum system in the presence of disorder, and having a phase transition in dimension over 2, so in 3 and higher dimension. Here also, it is believed that the upper critical dimension is also infinite. So
yeah, thank you. Thank you. And then when you spoke about two-dimensional system, it was Baxter-Wu model, three-spin interaction, which corresponds to two-dimensional Q4 POTS model.
That
Q4 POTS model, that's the second order phase transition with mean field exponents, but with logarithmic corrections, right?
Oh, no, it is not mean field. It is a different class. This is the four-state POTS universality class, actually, what you have for the four-state POTS. For the Baxter-Wu model, for which I show here, it is how to say, without logarithmic corrections, you have this exponents. Very probably that is the reason why it can be solved analytically, since you have no logarithmic corrections in that case, and also it is somewhat easier to make the calculation. If you look for this Turban model, but I showed just a minute, here. Actually, you can see that for m equals 3, you will have also a degeneracy of the ground the ground state, which is also 4 times. So actually, you could have that all the 3 are up, or 1 up and 2 down, and this could happen 3 ways. So then you get this 4 times degeneracy. And the corresponding classical system is actually in such a way that you have nearest neighbor interaction vertically, and horizontally this 3-spin product interaction. So, and this model is also studied numerically also, and one shows that very probably it has also logarithmic corrections. Actually, very probably the same type of logarithmic correction as the four-state POTS model. So this is what one expects.
Thank you.
Oh, thank you.
Okay. Professor Reinhardt?
Yeah, I have a question concerning the appearance of Kosterlitz-Thouless transitions. They are characterized by the correlation length, by the type of correlation length. And therefore, I have the question, if I compare random classical systems, or just quantum systems, or now random and quantum systems. In quantum systems, I have quantum mechanics, and I have correlations which are unusual. I would say I have entanglement. And is there any idea how this entanglement might be involved into the appearance of Kosterlitz-Thouless transition in the system you consider?
I think that at least I don't know any direct connection in that way. How to say, this is a long range model. If you have a short range model, you have not. Actually, we also calculated the entanglement in that model, and which was quite strange. that in the one-dimensional case, we observe no logarithmic corrections. You remember that in the nearest neighbor case, you have a logarithmic correction, and this which is connected with this effective central charge. And in that case, you have nothing. Actually, this type of phase transition, one can show that the renormalization group equations are very much similar to the random bosonic problem. So you know that the transverse field Ising model, it is a free fermionic model. And for this, you have this type of behavior, but for random bosons, the phase transition looks also Kosterlitz-Thouless-like. And actually, this type of diagram that I showed here, this is also looks very much similar for these random quantum bosonic problems.
Yeah, because I know it. I mean, if you have a usual order parameter with n dimensions, you know that if you go below n equal 2, you get this Kosterlitz-Thouless transition. So it must have to do with this, with n also. And in fact, if you may, well, I do not know if it also depends on dimensions and nearest neighbor interaction, if you may have entanglement between 3 states and so on.
Yes.
So and you have different behaviors. In one case, you have if you have 2 states, you have Bell inequality, but if you have 3 states, you have a very definite result between the classical and the quantum mechanical result. It's 1 or 0. I do not know which in one case, but anyway, there are different types of behavior of entanglement, I would say, if you consider 1, 2 particles or 3 particles and so on. And therefore I thought maybe this has also something to do in these models, but I don't know.
Okay, thank you.
Thank you very much.
Okay, thank you.
Okay, I guess I will have another question, but the time is out, so perhaps I'll send an email. And so let's thank Grazie.
Thank you very much.